No students are present, waiting for the students to come. Still waiting for students. We'll still wait for some time. After so many reminders in the group, students are not joining. Only one student, Rohit, joined.
Don't know, man.
Yeah, morning. Fine, we'll wait for 1 or 2 minutes more, right? And then we'll start.
Okay, man.
Fine, so let's start. Okay, so what we have done in our previous session, we have finished with the fifth unit, right? We have seen last at what is inverse filtering, what is winner filtering. This two filters, it is used for restoration of blurred image, right? Which is already degraded, and we are restoring, we are recovering our original image back, right? Noise reduction we can do with the different filters. That also we have seen what are the frequency domain filters, what are the spatial filters, right? We have seen so many filters in this. Mean filter, arithmetic mean filter, geometric mean filter, then harmonic filter, then the contra harmonic mean filter, midpoint filter, alpha trimmed filter. These were the linear filters, and in the non-linear filters, mean the statistic. Statistic order filter. For that, we have seen max, mean, median, and the other adaptive filters also. Why? Because generally what will happen, all the filters will behave in the same manner, right? Whatever the image is, they are not concerned about it. So when we are actually using adaptive filter, they are the smart filters, right? They will think like, if the situation is like this, then you have to do like this. It is something like that, right? So, in adaptive filters, adaptive median filter, adaptive average mean filter, whatever you say, those filters are actually checking some of the conditions first, right? And then and only then it will work further. That what we have seen. So this is how we have done with the fifth unit, and now we are going to start with the sixth unit, which is the color image fundamentals. Now we all know this thing that just looking at the normal image, which is having only few color shades of gray, right? Or if it is black and white image, you cannot see the contents, which is the detail of your image, right? If it is like that. But if it is the color image, right, then you can at least separate out the regions of your image, that. And our eyes also uh, used to with the color images, because every day in a everyday routine life we are watching the colors, right? Every color. So how we can see those colors? What is the reason behind it? How we can see the colors? Very lately joined, Shubham. Very nice. So there would be basically the white light only, right? That white light is actually reflected from the object, and the color will be generated. So what we can see the color in the particular, um, you can say, you have seen that that spectrum, electromagnetic spectrum, EM. You know that thing, right? So in which spectrum you can see the lights? Do you know this thing, Rohit, Shubham? In which particular region, in which particular spectrum you can see the colors? That's what I'm asking. Yes. No one is answering. Either say yes or no. I mean, if you don't know, then also you can say, Madam, I don't know. So I can move further. But I think you guys are not listening to me. Is it so? No. Okay. Fine. No worries. So we will see everything about this color image processing, right? So that is our sixth unit. So, what is the main two motivations in the color image processing? Because already we have seen here the processing in the grayscale images, right? Where we are having either white color or the black color, and we have the different gray shades, right? So it's a gray image. So now, what is the need of color image processing? What are the two motivations for doing this color image processing? So in automated image analysis, the color is a powerful descriptor, because if the color is like this and this, then the object should be like this. If we are talking about the vegetables, or we are talking about any other things, about the fruits or any objects where the colors are the specific one, right? The colors are the specific one, that if that would be the brinjal, it would be having a color of purple, or you can say violet, right? So if this would be the specification, that if the color is like this and the shape is like this, then it must be this object. So the color image, this color image processing, what we are doing, it is having a meaning, right? So simplify object identification and extraction, right? Because our main motive, do you remember that what are the cycle, what cycle we are following? The very first task is image acquisition, right? Then second task is image enhancement. Then what we are doing after image enhancement, what we are doing? See, this would be the interactive session, right? Otherwise you will get bored just to listen this. Yes. If my image is the noisy one, then I need to apply the filters, right? And I need to recover the image. So it is image degradation, restoration, right? Then if the here the color image is there, then you can do the color image processing. After that, finally you want to do what? Image segmentation, right? Because you want to recognize the object, because the whole image is not of your interest, just the part or the portion of the image is your interest. That is why you are doing this, right? So that image extraction automatically, that based on descriptor, if your object is identified, you can extract it, right? The human eye that can discern thousands of color shades and intensities, compared to about the 2 dozen shades of gray level, right? So um, just a minute. So here the two major areas. Here two major areas are there. One is full color and one is the pseudo color. Full color means just like our TV cameras or the color scanners and all, right? Where we are using this full color, because nowadays we are having the digital cameras and all the things we are having, because previously just before the 15 20 years, if you'll imagine, our life was like with the non-color TV, right? We were using that black and white TVs and all. But nowadays we are having all these things, that full color image processing, that what we are using over here. So pseudo color, that is what the particle monochrome intensity or the range of intensity means. It is not a full color, but the pseudo color. Few colors are only using into this. Few intensities are only been there, because if we will see first the color models, you will be having the RGB color models and CMYI models and so many models you are using, right? But if you will look for those colors, no, it would be, I mean, a vast range of the colors there would be, right? So that many color processing is not actually useful, right? Because every time you have to watch for all the intensities, and you need to convert that RGB three planes, and you need to calculate those things, and it would be a very huge process, and for that you need the more storage to store such kind of image and to do the processing, right? So you can even use this pseudo color. Then what is the color spectrum? What is it? So you know this figure, what this means. This is what the prism, right? And this white color light would be there. See, you need to join on time, right? Our session time is 7:30, and you guys are joining only for attendance after half an hour or after 40 50 minutes every time. This won't be allowed, right? Every time I know that few students are joining at the last only, and that I know. So I won't mark the present. If you wish to leave, you can. Already the message is passed yesterday only, right? So you can't say that you don't know, you don't aware of the classes, right? Already the message was passed yesterday night only, that from tomorrow there would be the sessions, and I've seen the message, so don't. Already message was there, no dear, then how you can say that you don't know this thing? If the message were already passed yesterday, how you can say you don't know about the morning session? Okay. In the Telegram group, just check and then tell me. Fine. So what is the color spectrum? What is color spectrum? You have already learned this thing into your, the school days, if I'm not wrong. If there will be a white light, and it will be passed through this prism, right? That would be divided into the six color range. Those six colors would be like violet, blue, green, yellow, orange, and red. But here the colors are not like exactly separated, right? They are not divided into only six range. It is just that these six colors are the main colors, and from one color to another color there would be a smooth blending. There would be a smooth blending of the color, that you won't realize that from one color to another color when you reached, right? So it is like that. So you have seen this electromagnetic spectrum, if you remember. Uh, Here these are the X-rays, gamma rays, ultraviolet, visible spectrum, infrared, microwaves, and so on, right? So here you can see in this, from this ultraviolet, this is your visible spectrum, this is your infrared spectrum. So our human eye, what the human can see the colors, that would be in visible spectrum. We have already discussed this thing at the time of the first unit, where we have seen all the different application of this rays, if you remember, right? So the human can only see the colors in visible spectrum, right? So we can see the colors like in the 400 to, they are the different wavelengths, right? And the spectrum, they are measured with the wavelength. They all have given this nm. Nm is nanometer, right? So in this range, 10 mm, and this 300 mm, 400, 500, 6, 700, 1000, 1500. So between this 400 to 700, you can say that this different colors are there, right? Before those and after those, there are only black color. You guys are joining so late. Matthews, it's already 8 o'clock.
Okay, ma'am. Sorry.
Yeah. So this is the wavelength comprising the visible range of electromagnetic spectrum. And now we'll see that what is the color spectrum. So in 1666, the Sir Isaac Newton, he has discovered this concept. When a beam of sunlight is passed through a glass prism, the emerging beam of the light that consists of continuous spectrum of the colors ranging from violet to red, not the white color, but this white color is converted into the different colors, which is divided into the 6 broad regions: violet, blue, green, yellow, orange, and red. No color in the spectrum ends abruptly, right? It is not like that they are sharply divided, okay? But rather each color blends smoothly into the next color, okay? Always. So that is why we have this different colors in a particular spectrum. Basically, the color that humans and some other animals perceive in an object are determined by the nature of the light reflected from the object, because some of the objects they are absorbing the color, some of the objects they are reflecting the colors. So based on that reflection, absorption, the color will be generated and the human eye can see that color, right? So this is what you know already in your physics. So green objects that reflect the light with the wavelengths primarily in 500 to 570 nm range. You can check. 500 to 570 nm range, the green light would be reflected. So while absorbing most of the energy at the other wavelength. So other energies would be absorbed and only the green color will be reflected. So green objects reflect the light with this wavelength. So you can see that color as green. Okay, because all the other wavelengths, they are simply absorbing. They are not reflecting. That is why. So if the light is achromatic, means void of the color. You know, na, achromatic and non-achromatic, that is known as chromatic. The chromatic word is used for the color. It is having a color. And achromatic means no color, void of the color. So if the light is achromatic, then its only attribute is its intensity and amount. That is what we have seen in our 5 units, like the black and white television. That is what the example. It is only having the color either 0 or 1. Or if it would be further enhanced, you can say it would be having gray shades, few of the gray shades, but it is not having any color, right? But if we are talking about the chromatic light span, the electromagnetic spectrum from approximately 400 to 700 nm. This light would be there between 400 to 700 nm, and we can see the different colors. Okay, so till this, I hope everything is clear. David, you have joined at 7:30, then you left, and then you are directly joining at 8. What is the reason? Ryan, just join now. I won't mark the present for you guys, because I need to be strict. Otherwise, you won't attend the whole lecture. I cannot give you attendance every time.
Ma'am,
Hmm.
I joined late. I'm sorry, but
Every time when I'll check at 7:30, you guys won't be there. When at the time of 8:30, but in this much strength, I cannot actually identify. But now I'm actually identifying you guys that who are actually joining late.
I don't usually join late, ma'am.
The session timing is 7:30 and you are joining at 8, so it's not late, is it so? Okay, fine. So the another things about the colors. What is here the visible light? So relatively narrow band of the frequency in the electromagnetic energy spectrum. Narrow band of frequencies in the electromagnetic energy spectrum. And what is the color perception? What is color perception? The colors that human beings perceive in an object are determined by the nature of the light reflected from the object, because whatever the wavelength, the other color wavelength, that would be absorbed, and only the color the object is actually having, that will be only reflected. So you can see the color. So some shades of color, like a body that favors reflectance in a limited range of the visible spectrum. White color, a body that reflects the light that is balanced in all visible wavelength, right? White color won't be reflected or absorbed. It is the balance, right? Which is only the white color. Right? See this. This is what illumination, the light source, right? And if it would be there onto the object, right? Then and only then, particularly red color wavelength. So what it could be, red color wavelength almost from 600 to 700, or you can say 650 to 700, because this would be the orange color, right? Red color after 650, suppose. So that color will only be reflected and all the other wavelengths will be absorbed. Say yes or no, right? So our eye can see this color, that okay, this is what the red object. Same case if the white light is there, right? Here if this is what the green color, this green color will only be reflected and all the other colors will be absorbed, like the red, orange, yellow, blue, green, not green, except all the colors that will be absorbed and only that color will be reflected, right? Are you getting? Yeah. So here the color can only exist when the three components are present: viewer, object, and light. So this is our viewer, means we can see the object, then object and the light. When the white light hits an object, it selectively blocks some colors and reflect the others. Only the reflected colors contribute to the viewer's perception or color. Only reflected colors, absorbed color, we cannot see, obviously, right? Achromatic light, its only attribute is intensity or amount, that what we say. So viewers can see on a black and white television set. The term gray level that refers to a scalar measure of intensity that range from black or grays and finally to the white. So means we'll start with 0, that is black, then intensity will be increased. So they would be the different gray shades like dark gray, dark, 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 then lighter, 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 and so on. And finally it will reach to 255, that is your white color, right? So that is your achromatic light, which is not having any color. But if we'll talk about the chromatic, it will be having color. So this is what about the chromatic light. The electromagnetic energy spectrum from approximately 400 to 700 nm. So how you can measure this, or what are the different factors? So in the very first unit only, you have seen these terms: radiance, luminance, and brightness. Brightness that we have discussed, we cannot measure the brightness. Do you remember that? But we can still consider this radiance, this luminance in watt and lumens, Lm. So what is radiance? The total amount of energy that flows from the light source. It means that is your illumination. From here to here, the total amount of energy that flows from the light source, that is known as radiance. That will be measured in watt. Now what is luminance? Luminance means a measure of amount of energy an observer perceives from the light source. A measure of amount of energy an observer means what we can see. This would be luminance. This. An observer perceives from a light source. And what is brightness? Brightness would be subjective descriptor that is impossible to measure, that we know. The achromatic notation of intensity, one of the key factor in describing the color sensation. What is the brightness? Suppose I'm saying you wear a very bright clothes today, so it would be a bright color, dull color, right? So this is what the subjective thing, right? Bright colors, light colors. So we are also saying bright pink color, light pink color. So in even into the pink shade, we have the different notation to say, right? Whether it is dull pink or bright pink, baby pink, okay, simple pink color. So that is what subjective descriptor, how you are describing that color. Now you can see this, what you can see here. Absorption of the light by the red, green and blue colors in the human eye as a function of wavelength. How you can see blue, green and red color. This is what absorption, arbitrary units. This is the different range of the colors, like 400 is bluish purple, at 450 you can say it is like the purplish blue, that is known as violet. This is blue, this is blue, green, green, yellowish green. Here together, this is only yellow, only orange, this is reddish orange. It is not purely red, it is not purely orange, but it's blending of orange and red. And finally red after 650 to 700. So this is what blue wavelength, right? That would be at 445 nm. So it would be a high peak where there would be a only blue color. Here this is what the green at 535. Otherwise gradually it is increasing. Here very, near to green color would be there. Then it would be increase, increase, increase. So here the quantity, or you can say the color intensity would be high now here, right? And then again gradually decreasing. Here again there would be a mixture. It will, because the red color will start appearing from this 450. but intensity is very low. But here it is at the peak at 575 or somewhere, and then it's like this. So red color starts from this, but blending of yellow and orange, blending of yellow, it will make it as an orange, right? And then here the green color, it's totally over and it's only red is there, right? So it is just a combination of different colors. That is why we are having this spectrum, right? You can draw at least this figure, and you can write into whatever you understand in that term. There would be a light source, the energy would be there onto the object will reflect only that particular color wavelength, and the other color wavelength would be absorbed. So that thing you can write into your own language. Please write it down. Done? Then you can write about this, what is radiance, luminance and brightness, just below that figure. So you can imagine what is radiance, luminance and brightness. Yes, what you are asking, Matthews, is this invisible spectrum. This is what I already explained. But you joined late, no? Of course, this would be invisible spectrum, right? Because human can see only in visible spectrum. Some birds are even able to see in ultraviolet, if you heard somewhere. I don't remember exactly, but few birds can even see into ultraviolet spectrum, right? But the human can only see in visible spectrum. Fine. So here you can say approximately 66% of these cones are sensitive to red light. Have you seen this? 66% from this to this. And here there's only 33% to green light and 6% to blue light. 6% for blue light and the 33% for green. Because here almost, red color is over the green, right? So green color is very less in the spectrum, right? Only this many percentage it will occupy, blue very less, and almost all covered by red. So this is what the observation which is there given in the book, right? Absorption curves for the different cones have been determined experimentally, and strangely, this do not match the CIE standards. Whatever the standards given by the book, and whatever the experiment they have done, they doesn't match with the standard, because here for the red it's 700 nm, for green it is 546 nm, and for the blue it is 435 nm light, as the standards were developed before the experiments. So they have given the standards, but when they are actually checking for this, no, this would be different, right? So experiments are saying some different wavelength, and the book is saying some different wavelength, right? For the red, they are saying 700 nm, but it's actually 575 nm, right? For the red, it should be actually over here, this red color. So CIE standards and these experiments, they both are saying the different thing. Now, the primary color of light. What primary colors you have and what the secondary colors you have onto the light. So we'll see some color fundamentals, and then we will move on to this, the different models of colors. Right? So our actual topic, our actual syllabus getting starts from color models. Right? To start from the color models. But those are the things which you need to know about the colors first, right? That is why we have seen this, all the things. Okay. What are the primary colors of light? They are the red, green, and blue, right? So according to the CIE, specific wavelength, values to the three primary colors should be 435.8, green 546.8, and red 700 mm, according to the book. These are the wavelength where these colors are visible. Okay. But here it would be somehow mismatched, right? But that's okay. No mean that this three fixed RGB components acting alone can generate all spectrum colors. It doesn't mean that only primary colors can generate all the colors. No, secondary colors required, right? So secondary colors of the lights are cyan, magenta, and yellow color. Magenta, it makes with this red and blue, then cyan means green and blue, and yellow means red and green. Mixing the three primaries or the secondary with its opposite primary color in the right intensity will produce the white color. How? That we'll see. The primary colors of the pigments or the colorants, that is cyan, magenta, yellow. A primary color of the pigments is defined as one that subtracts or absorb a primary color of the light and reflect or transmit the other two. It means what? Here the primary colors are actually absorbed. Okay. So reflected would be this cyan, magenta, and yellow, because that is totally opposite to RGB, right? And the secondary color of the pigments or the colorants, that is red, green, and blue. So the combination of three pigment primaries or a secondary with the opposite primary will produce black. So that you can see over here. Now you can check this, and then we will see that again. This is what your red, green, and blue, right? This two will R plus G means red plus green, that will be yellow. Then red plus blue will create magenta, and blue plus green will create cyan color, right? So this is what the mixture of light additive the primaries, and this is what subtractive primaries. In a few of the models, they are using that subtractive primaries, and that is why we are having that, that Xerox machine and all, right? Xerox machine, whenever we are having the white paper and we will have the Xerox, it will create all the black colors and all, right? So that what it is used in Xerox machine. wherever we are having a different colors, but we have black and white print, right? So accordingly it will generate the black color. Fine. So this is what magenta is red and blue. So for red and blue there would be the color wavelength. For green it is null. Same way for yellow you can check. For red and green it is up, and for blue it's down. This is only for a single color, red. If there would be a red color, all the other two colors will be suppressed. Very simple to understand, right? Yeah. When I'll get to know, I'll pass the message. I even don't know. Shubham. Fine. So here you can see this is what your image, illumination into reflection. This is what your basic model, right? Basic image model. So if the light is there, right, here the particular color will be reflected, all the other wavelengths will be absorbed, and that whatever the color is there, that will be reflected to the eye, right? So if there would be a white color, you can see that is a white color. No color will be there. So this is what primary and secondary colors of light and pigments, courtesy from this. This is what the copyright image. So now you can see this here. The perfect addition of the colors will generate this white, and this is what the perfect subtraction, mixture of the pigments, it will give you the black color. So we were talking about that only. If you will subtract, I mean, here you have the primary colors magenta, yellow, and cyan, right? And then it will generate here like a red, green, and blue, right? And here in between this, we have in the subtractive black color, in this additive we have white color. They are the different models, right? Primary and secondary color of light and pigment. So again you can check this. Primarily, these are the primary colors of pigments and colorants. Cyan, magenta, yellow. The subtract, I mean, see, the primary color of pigments is defined as one that subtracts or absorb a primary color of the light and reflect or transmit the other two. The combination of three pigment primaries or a secondary with its opposite primary produce the black color. Otherwise, it will produce the white color. You can see this. Right? So that's all for today, I think. We will see these characteristics of colors, that's hue and saturation and all. That would be in the next lecture. Today, very few students are here. So that's all for today. You can write your enrollment numbers and you may leave. Many students have joined at the last, so I won't mark them present. So don't ask me why I was absent, though I was present. You can write your numbers and you may leave. You can write your enrollment numbers and you may leave the meet.